Can slowly start. So yeah, welcome everyone. Today we're very happy to have Robert Kramplin from Heidelberg University, and he's going to be talking about moduli spaces of twisted maps to smooth pairs. Please.
Okay, great. Yeah, thanks a lot for the invite. This is exciting to do, and it's exciting to use this fancy technology and see everyone at the same time. So, yeah, and feel free to ask as many questions as you want throughout. So, I'm going to be advertising a lot of different areas, which I think are exciting. So, you can, if there's something I say and people want more information, you can divert the talk towards that. So. Um, okay, great. So let me just start with some motivation. So what I'm going to be doing is I'm going to be looking at the geometry of smooth pairs. So what I mean by this is like I fix X, which is some smooth projective variety, and D is going to be a smooth divisor. So it is going to be very important that it is a smooth divisor, not something more general, but we'll talk about that later. And maybe an interesting invariant of these guys is you want to count maps from curves to this target variety, and the curves have some marked points, and I want to fix the tangencies of the marked points to the divisor. So here I have some map from a curve with n marked points, p1 to pn, and let's say we fix some tangency ci. So ci is just some natural number, and I want pi to be sent to the divisor d and with tangency order ci. So, and I say as well, there's some other kind of discrete data we can fix throughout. So I can say I want genus 5 curves or genus 0 curves or whatever. I want to fix a genus, and maybe I want to fix the degree of the map as well. But throughout, I'm kind of always going to fix that, but I'm not going to write it down at the time. But there's some discrete data. Um, so here's an example problem you might want to ask is, well, okay, what's a nice smooth pair? Well, I could take XD to just be P2 and D to be a smooth cubic E. And then maybe I want to count rational curves, so genus 0 curves, um, with one marking um, and maximal tangents. So it's kind of maximally tangent to E. So here's a picture as well. This is my E, and I want to count these rational curves which intersect E in one point. So this is like the image C. Um, So that's just some problem you can set up. And actually, okay, there's an answer to this problem, which is the the number is just actually the number of flex lines, liquid flex lines, which is equal to 9 in this case. So um, one way of seeing this is that if you pick some base point on E, you can view it as an elliptic curve, and these flex lines are 3 torsion points. So there are 9 of them just from theory of elliptic curves. Um, So that's great. That's our first invariant. But I guess in general, like this is very hard to do by hand, and like you're not just going to be able to write down all the maps explicitly and say, oh, if even if there's a finite number, it's not so obvious what they are or what the number is. So um, there's a general framework for this, which is so-called Gromov-Witten theory. So I guess I'll write GW theory. Um, and well, what does this do? Well, the idea is you want to set up a space of such maps, and you want to encode these counts as certain integrals on this space. Um, and somehow the geometry of this space of maps is going to give you ways to get a hold of what these numbers actually are. So let's define a moduli space. So I'll write M circ lambda x rho d, and I'll explain the lambda in a minute. So it's going to be a space of maps. I guess, as above. So I guess from these. Which are so-called dimensionally transverse to D. So I should have given myself more room here. That's too optimistic. Transverse. So what that basically means is that so C in general is allowed to be, have multiple components as a nodal curve in general. And what I want is that no component of the domain curve falls completely within the divisor D. So in other words, basically, the pre-image of the divisor D under the map is just a bunch of points. And yeah, so it's some dimension 0 locus. And the reason I want to impose this condition is that I can actually make sense of what tangency means in this space. So I had these tangency or CI, which I'm kind of encoding in this green lambda. So throughout, I'm going to write a sub lambda, and that's just collecting all of this discrete data I said I want to fix. But in particular, a part of that data is these CIs, these contact orders. So the CIs are always in this lambda, along with the degree and genus and stuff. So why does tangency make sense in this space? Well, what I can do is I can take a section, cutting out the divisor SD, and just pull it back via the map. And the point is that this is non-zero because of the dimensionally transverse property. Because if you imagine like, hyperplane including inside of like a hyperplane inside of P2, if I pull back the section defining my hyperplane, I just get 0 because it's, yeah. And so if I pull this section back, I can write it in the following form. I can write it as a product of SPIs to the CIs, where SPI is, say, a section of a line bundle on the domain curve C, which cuts out the point PI. So this is just another way of saying, okay, F vanishes our PI to order CI. And yeah, this is up to unit, but that's all okay. Great. And so basically, yeah, I can define the space of such maps such that this green condition holds, and this is this M circ XD. Okay, great. But there's a problem, which is like at the end of the day, I wanted to encode these enumerative counts, and I said I wanted to do some integrals in this space to do that. In order to get well-defined integrals, I really need a compact space, a proper moduli space. And this moduli space isn't compact. So we've got M circ lambda x rel D is not proper. So actually, I can't really make sense of like an integral in this space because an algebraic geometry is a proper push forward to a point. So I can't get some invariance from this. And like, so here's a way of seeing this is, let me draw a tiny little schematic picture. Here's X, here's D, and maybe I'll use a different color. Maybe this red line here is like the image of my curve. So maybe I have CT, which is like a family of curves. And maybe as t goes to 0, so it's very small, the image of this family becomes the divisor D. But so it's kind of like it's dimensionally transverse through all t, but kind of in the limit CT equals D and it's not dimensionally transverse. So that's just saying if you can come up with some situation like that, the space isn't proper. So the story of this talk is going to be a way of compactifying the space, of then studying the geometry of what the space actually looks like. So yeah, this motivation about these enumerative counts getting some interesting variants are yeah, so that's really the motivation. But if you don't care about them, there's an interesting moduli space which has some cool geometry. So great. So the compactification originally was just defined by some work of Charles Cadman and Abramowitz using work of Abramowitz and Vistali. So the compactification I'm going to talk about is called twisted stable maps to a root stack. So I'll elaborate on like what this is, but there are two ingredients. So the first ingredient is actually we're going to replace X with a new object. So replace X with something denoted by XDR, which is called a root stack. Okay, I'll talk about that on the next page. And then we're going to look at certain maps to XDR, but now we're going to allow not just scheme theoretic maps, but somehow maps from curves with a little bit of stacky structure. So there will be finitely many points in the domains which are decorated with like a cyclic group. And that extra data is going to be like key to compactifying. So we're going to replace kind of the domains C with, so I guess I'll write curly stuff for anything which has this extra finite group decoration, a stacky structure. and these will be called twisted curves. But yeah, you don't have to know what they are. I'll give you kind of the key points on the next page. Great. So let me address the first point. It's like what are these root stacks? So there is some
Can I ask
auxiliary
a
data.
question?
Of
Can I
course.
ask about so you want to parameterize maps with order exactly Ci or a multiple of Ci?
Mhm. Oh yeah, good question. So I want to say maps with exactly tangency Ci at Pi. Yeah.
Oh, okay. Okay, thanks.
Right, yeah. So imagine I set like Ci to be 1, and like I was looking at like maps to a projective space for like P2 relative a hyperplane. I genuinely want to then look at like basically lines in P2 transversely intersecting that hyperplane and not multiple covers of that, for instance.
Okay, thanks.
Yeah, great. Cool. So yeah, so what we do in this story is we first pick some natural number R, which is we're going to call a routing parameter. And let me just draw a picture of like what this XDR is. So here's our original space X, and inside of it is some divisor D. And XDR is going to be some new space, which is over here. And it admits a map I'll call pi to X. And there is some locus in it, which I'm going to call 1 over R times D. And the property of this map pi is that it's going to be an isomorphism onto X away from this divisor. So it looks like we've cut out the divisor D and we've added in something which is I've labeled 1 over R times D. So it's like a new compactification. And the point is that this locus here, every point in this 1 over R times D is now decorated with a mu R. So like R fruits of unity. Every point now has this finite group attached to it. So XDR is now stacky, precisely on the locus above the divisor we started with. But so yeah, so somehow it looks like there is a definition. If you want, I can tell you, but I think the picture is the key point. And let me just justify where the name root stack comes from. So this XDR comes with a canonical line bundle section pair. So I'll write this as O of 1 over R times D and S of 1 over R times D. So this thing I labeled 1 over R times D is some Cartier divisor on this space, and it has a section and an associated line bundle. And it satisfies some nice property, which is if I pull back my original line bundle section pair downstairs, so O of D and SD, this canonical guy upstairs is an half root of this. So this is isomorphic to O of 1 over R times D, S1 over R times D to the R. So it's a construction which is like a kind of universal way of adding in roots to line bundles and sections. So that's kind of the universal property defining XDR. Cool. Any questions so far?
Is there a relation between this and cycling trick?
Oh, sorry, could you say that one more time? Any relation between this and
cyclic trick that makes line bundle with I don't know how to say.
So cyclic. Sorry, maybe it's my internet slightly bad, but you said cyclic something.
Cyclic covering trick, I think is what.
Yeah. Thank you.
Sorry. I mean, honestly, I don't know what that is. Maybe you can tell me after, and then we can chat about it. I mean, so I will just say like maybe this will help answer your question. Is like the way you construct this XDR is you Okay, so here's the local model. So if X was like spec A, so maybe I'll write this here. So it is related to cyclic covers, which are somehow ramified precisely along the divisor. So if you have X is like spec A, the local model of XDR is where you take spec of A adjoint some new variable T, quotiented by the relation T to the R minus SD. So SD is the section cutting out the divisor, which is just an element of A. And then there is so this guy here really is like a, it maps to X as like a some degree R cover. But the point is that you can quotient this further by some mu R action, where mu R acts on T by multiplying by the R roots of unity. So this big block at the top is what XDR is. So it's some quotient of a cyclic degree R cover by the roots of unity.
Okay, I see. So there's additional quotient than
Yeah.
what? Okay, thank you.
Okay, thanks for the question. Yeah. So the reason you take this quotient is because otherwise this line bundle section pair wouldn't be canonical. So somehow on this A adjoint T mod T to the R minus SD, there are line bundle section pairs which are fruits of the guy downstairs, but the section there are different sections, right, corresponding to the different roots of unity. So somehow it's like a weird construction which glues all of those together. Yeah, great, thanks. Cool, yeah. So root stacks come up a lot in like various places. So you don't even have to care about these enumerative invariants to want to study them. They come up with a lot of moduli theory. But yeah, for today I'm going to be looking at maps to them. So the overall moduli space we're going to be interested in, I'll write is orb XDR, and it's going to be a space of maps. So I'm just going to draw some picture of what it is. So I'm going to be looking at maps from curly C to XDR, where these curly C's are now curves which kind of have finitely many stacky points, perhaps at the nodes. And these stacky points really are just kind of, they have additional data of mu R roots of unity as like automorphism. So these red points are all sent to the divisor, to this kind of new stacky divisor in the root stack. So there's a bunch of conditions to properly say what the space is, but think of just there are curves with some marked points, and they have finite roots of unity, and they map to this new target, which also is decorated, or some of the points are decorated with roots of unity. And let me just say, like, there's this lambda which is still here, and this should be saying encoding tangency somewhere in this definition. So where is tangency? Well, tangency comes from as follows. So if you're given one of these maps, so I guess, or maybe it's on the next page. Okay. Okay. So if we're given one of these, so I guess let me redraw a picture of the domain, something like this. And maybe there's a marked point which has this mu R. This is the domain curve C. And let's suppose it's sent to this like divisor upstairs. A part of what one of these morphisms is, if you spell it out, is you get a group homomorphism from mu R on the domain to kind of a mu R on the target. And well, what does that look like? It just looks like an R fruits of unity is sent to a power of an R fruit of unity. And we enforce that this power is the contact order we want. So we're now basically encoding contact orders via these group homomorphisms. So we're in this definition of the space, we are saying we want to take the maps from these stacky curves to this root stack such that the induced group homomorphisms look like this. And okay, the claim is that somehow this actually does capture the tangency of the original problem. So here's a fact is that if you take R big enough, so basically R has to be bigger than the contact orders, there is an embedding of the original space that we cared about, M circ of X rho D, inside of this space of maps, of twisted maps to the root stack. And not only that, there's this orbifold space. So it's like orbifold space for orb. That's now compact. So we've kind of solved, I guess, Charles Cadman and Abramovich and Vistali have solved our original problem of compactifying. And now we can just, we can do what we want. We can define invariants by integrating over this space and get interesting numbers. So that's all this means, is that there are some associated invariants called Orbifold-Witten invariants, which are integrals over this space, sorry, yeah. And you can, that's well defined now. So here's kind of what I'll talk about for the rest of the talk is there are interesting properties of these invariants which seem to be like universal, like independent of X and D. And there are funny structural things which just happen to hold. So what I want to do is like we want to study so-called universal relations on, I guess, on these spaces, which tell us the general structure of these integrals. So the general structure of orbifold GW invariants. So just these integrals. Okay. So here are a few examples of this which are known. And so Tseng and Yu over the last 5-ish years have shown that these orbifolding. So I guess like here's a key point actually, is that in this theory, right, there is this parameter R, this routing parameter, and I didn't say what to pick. I just said take it big enough, and it's some choice. So you should think that these invariants here and the moduli spaces themselves is not a single moduli space, but really a family of them as I vary R, as I vary this routing parameter. And so you can look at these invariants now as a function of this parameter and say, what type of function is it? So what Tseng and Yu said is that these integrals actually do depend on R, but in a very nice way. So these integrals are polynomial in R, and they write down the degree in terms of the genus of the domain curve. So this is some discrete data hidden in lambda, but in the notation lambda, but it's of degree less than or equal to the max of 0 and 2g minus 1. So yeah, so they are polynomials, but in just the max is there just because of the genus 0, it should be constant in R. Yeah, so otherwise it's 2g minus 1. But even before Tseng and Yu, yeah, genus 0 was studied, and it was shown that, well, okay, these are constant, which is implied by the result above, but they're actually equal to some other known invariants. So I'll just say orb GW equals some other known invariants called logarithmic Gromov-Witten invariants. So people can ask me if they want, but the point is there are alternative compactifications of this original space here, this transverse locus, and they give rise to different invariants because we can do integrals in that space. And one of those compactifications is so-called log stable maps. But the point is that this is studied and interesting for various reasons, and it turns out the invariants just agree in genus 0, but not in higher genus. And so the way these were shown, these two, well, I guess the way the green result was shown by Tseng and Yu was like an involved kind of degeneration localization. So like some fancy computational techniques in enumerative geometry. And he did some hard computations and it kind of pops out. I mean, okay, it's very cool how they do it. But it's a little bit mysterious. So what I want to say for the next like powerish is like why kind of geometrically these invariants should be polynomial in R and how you can recover these results. So what I'm going to, so we want to give a way of seeing these from what I'm going to call the universal space. So I'll explain what that is now, but there's another space somehow controlling the geometry of all of these orb XDRs for every single X and D. And the geometry of that space will give some explanation. Yeah, I'll pause for questions for a second if there are any.
Maybe can you say about this orb XDR? So is the idea that you're trying to parameterize exactly the morphisms from curves to X with tangencies exactly CI instead of multiples of CI?
Yeah.
And if so, is this like some kind of closed substack of the root stack or something like that? Or is it, I mean, doesn't the root stack parameterize just all the morphisms with tangency multiple of CI somehow?
Oh yeah, sorry. So I guess it's not closed. So this guy doesn't live inside of a root stack itself. Like the root stack you should think of as like the target. And like this space has like lots of additional information, like it's a map from a curve to this target. So it has like all the data of like various curves and their maps to the target. So it's so yeah, maybe I should say so a point in this space is like a map from some curve to the target. So it's a map from some genus G curve to the root stack. So it's going to be much bigger than it's going to. Yeah, so the dimension and stuff of this space is going to depend on the dimension of the target, but in general, it's like much bigger.
Okay, so it's more than just parameterizing morphisms from curves to X, not the root stack X with tangencies exactly CI. It's more than that. You know what I mean?
Oh, sorry, maybe sorry. What you just said sounded exactly right, actually. So yeah,
okay.
It's morally parameterizing curves with precisely those tangencies, and kind of the generic locus is precisely that, but then there is some weird stuff that happens in the boundary. So that's what
I see.
Morally. So, because it's a bit mysterious. Like, I said, like now we can add some stacky structure, and now the tendencies are encoded by group homomorphisms, and I guess maybe the point is that like even when you have the degenerate case where you map your curve solely inside the boundary divisor, these group homomorphisms are still you still have them, and so you can still enforce that they are given like this, and that's kind of why the compactification works. Like you don't need to assume transversality to say I want the group homomorphisms to look like this. But yeah, you're right. Like it's a bit more mysterious what like kind of that locus is in the moduli space.
I see. But then maybe still generically true on the generic locus that you get something which looks like a close substack of the root stack, or maybe not. Maybe close is not the right word. That's my question, I guess. Like because if this parameterizes morphisms exactly CI and the root stack multiples of CI, is it like?
Yeah. So okay. I guess like yeah. So there is some like open locus inside of the space which looks like maps with precisely the right tangency to X at D. And then the complement of this space inside of this space is just like something, which I'll talk about. But yeah.
Okay, I see.
But yeah, thank you.
Thank you. Thanks.
Great. So yeah, so what I'm going to do actually, I'm going to throw away all, I introduced these spaces, and I'm actually going to throw them away and talk about a different space, but they're very much related. So let me tell you what this universal space is. So if there's going to be a forgetful morphism from this space orb lambda xdr to a space which parameterizes, so its points look like a curve C, along with a line bundle and a section on C. So line bundle section pairs on curves. I'll be more precise what this right-hand side is in a second, but what should this forgetful map be? Well, I said a point in the left-hand side looks like a map from one of these stacky curves to XDR. And I also said that XDR has this kind of canonical line bundle section pair. So basically all I'm going to do is pull back this line bundle section pair to C and just remember that information. So I'm going to map this to the triple curly C with the pullback of what I call O of 1 over R times D, S 1 over R times D. And this right-hand side is kind of parameterizing all such triples that could arise from this type of operation. So in particular, like it's not dependent on X and D, so somehow it's just a very big space. And this space is I'll denote by orb lambda curly A sub R. You should just think of this as notation. But this is what I'm going to refer to as the universal space. Universal because now there's only a dependence on R and the like discrete data, so basically the contact order is lambda, but it doesn't depend on X and D. So all of these different orb XDRs map to this one guy. And this is a thing which actually, like, it seems like a really big space, like how it seems quite complicated, but what's going to happen is that actually it's very like combinatorial, and you can understand the geometry like really explicitly. So okay, the stuff in the red brackets I won't talk about, but it's like actually a space of maps to some other thing, but yeah, don't worry. So it's a space of maps to some stack like A1 mod GM, but that's just because a map to A1 mod GM is a line bundle section pair. So there's some way of encoding it like that. But I guess the important thing is like this universal space here, you should think of as just parameterizing triples, twisted curves, so one of these stacky curves, a line bundle section pair, where the twisted curve somehow is the kind of groups are labeled by these mu r's, so R just tells you how stacky it can be. And the line bundle section pair is somehow like it's limited of how stacky of a line bundle it is, basically, because it should be pulled back from the core space if I take the half tensor power. So what I mean by this is that this any twisted curve has a map to an actual scheme theoretic curve, basically just forgetting the group isotrops, these mu r's, and just forgetting the stack structure. And under this map, this line bundle should be pulled back via it. So that's giving some kind of criterion on which line bundles and sections appear. Okay, great. Yeah, maybe I should pause for a second. Any questions? Oh, sorry, I missed a blue box. Maybe, yeah, okay. That blue box is something I should have written in, because I was going to say as well, yeah. So let me just summarize a little bit more what these line bundles are. Because this right-hand side, I said, still depends on lambda. It still depends on these contact orders. So how do I make sense of contact orders for a line bundle section pair on a stacky curve? So let me just spell that out. So contact orders. Well, here's the idea is that if I have a line bundle, so here's a little picture of my stacky curve. It has this mu r point, and I have a line bundle on this stacky curve. So here's a C. Oops. And I have a line bundle on this guy. We can always take the like this, the stalk of a line bundle at a point. So maybe this red thing is point pi. I can always look at L restricted to the point pi. And the point is that like, okay, in usual scheme theory, this is just, like a one-dimensional vector space. But now in the stacky world, this data inherently is a one-dimensional vector space with a representation of this group mu r. So this is a one-dimensional representation of mu r. And well, what is a representation of mu r? It's just specifying the weight for which the R fruit of unity acts by. So you have these kind of R choices of characters, and it's just a choice of one of these characters. And we are enforcing, so enforce this representation is of weight Ci. So maybe that Ci is not readable, but the point is that yeah, Ci is just some number, and I'm saying that the R fruit of unity has to act by that weight. And so that's a new way to interpret these contact orders now in this space. Cool, yeah. So that's really the key point, is that you got these line bundle section pairs on these stacky curves, and the contact orders are telling us for representations of on the fibers of these on the stalks of these line bundles. So there are some constraints. Great. So okay, great. So now let's try and make this space a bit more down to earth, because that was like quite an abstract guy, and its systems a really big space. And the point is that it's controlled by some tropical geometry or combinatorics. So let me show you for an example. And I can draw some pictures of like, I'll try and draw some pictures of curves. So sorry for my let's see. Maybe. So here's a picture of my stacky curve C, and or maybe I'll actually, sorry, maybe I'll make these in green. So I have 3 components, one of genus 1, 2 are, I guess, rational, and I have 2 marked points. So n is 2, and that's P1, P2. And these 2 marked points, P1 and P2, I have some kind of mu r's attached to them, and also these nodes could have some groups attached to them. So I'm going to assign to this data something combinatorial. So the first thing I'm going to do is take the dual graph of this curve. So I'm going to write this as follows. So like, so I have a vertex for every irreducible component, and inside the vertex I put the genus of that component. So I've got 1 genus 1 and 2 genus 0, and for every node I have an edge between those 2 corresponding vertices. So yeah, maybe to color code it, these edges in green correspond to those 3 green vertices. Oh, okay. Didn't like it, wanted me to disconnect. Okay. Great. And I guess also for these 2 marked points, I should add in 2 legs, so they're kind of like unbounded rays attached to the vertex they lie on. So these 2 yellow guys correspond to P1, P2. On top of this, I have a line bundle and a section pair that I haven't told you about. So on this picture, I have some line bundle and a section. And what I'm going to be interested in is where this section identically vanishes. So let's pretend that the section is identically 0 on this genus 1 component, but let's suppose that the section is not identically 0 on like either of these 2 rational guys. So with this extra information, I'm going to put I'm going to draw a symbol next to each vertex. So I'm going to draw a plus here and a 0 here in red. The plus corresponds to if the section is identically 0, and confusingly, I put a 0 when it's not identically 0. So like you would probably think like, what the heck is he doing? Like obviously it's the wrong way around. Why wouldn't you write 0 for when it's identically 0? Somehow it's the right way around because of I've done some dualization, and from a perspective of tropical geometry, this is correct. But I agree it's confusing. So 0 means on the right-hand side means kind of non-zero on the left. And a plus means 0. Yeah. So this type of picture is what I'm going to call a mod R tropical type. So there is really some other data I can draw on this picture. I'm just to save some time and not make it so fiddly. There are some slopes I should associate to each of these edges. So that I've kind of got the formal description below. So bullet point 1, 2, 3. So I have a graph, a labeling 0 or plus to each vertex. Then I have some edge scaling factors. So basically I have an integer modulo r for each of these green edges. And that's somehow constructed from, again, the representations of the line bundle at the nodes, because the nodes can be stacky, you can get interesting representations. I'm just recording that separately. It's not so important for us in this talk what they are, but yeah, there's some more numbers you can construct, and they should be drawn on that picture. And okay, here's a bit of motivation. If you've seen some kind of tropical maps before, is you should think of this somehow as like arising from like a map from a graph, like a tropical map from a graph to a circle. So this circle is R mod little r z, and kind of unusual tropical geometry, the usual tropical geometry, people consider maps from like graphs to array. And basically what's happening is that, well, okay, a vertex either maps to 0 or it maps to the interior of array. And that's what the 0 or plus is encoding. So it's morally related to this. But yeah, so there isn't actually a map from the graph to a circle here, like a canonical one. But it looks like this information is induced by a map to a circle. Cool. Yeah, any questions?
So this mod R tropical type graph somehow depends on R in a way that is not visible in the picture, or?
Yeah, that's a really good question. So yeah, so I guess yeah, so your question is like, where is R here? Yeah, I guess one reason it doesn't look like it depends on R is because I didn't really write down what these kind of slopes are. So there are some slopes which there should be some integers modulo R on the slopes, and what you can label with depends on R. But the kind of underlying like what I've drawn doesn't look like it depends on R, but the only R dependence is on the slopes, which I was too lazy to write down. So yeah, you're exactly right. Yeah. So bullet point 3 is the only place where kind of R pops up. It's just they live in the cycle of order R.
Yeah, great. Thanks.
Oh yeah, maybe I should say So I guess often I will denote. Well, it's a pencil. I won't denote it like that. I'll denote these kinds of pictures, these types, as like a tau in a square brackets. People often, there is a notion of like an actual tropical type, which is usually written as a tau, not in brackets. So, and I should say as well, if you have like a genuine tropical type, so something from usual tropical geometry, if you've seen that, you can reduce it modulo R and get one of these guys. So that's kind of the notation. Cool. So what's the use of this is that, well, I'm going to stratify my space now, this space of twisted maps. Oh, sorry, the universal space even, in terms of these types. So I'm going to define a locus, z tau circ, which is just the locus of guys CLS, which induce like the picture corresponding to tau. So which induces type tau. So basically, yeah, so for every triple CLS, I can draw a picture just like on the previous page. And if that picture, as I vary over CLS, which induce a fixed picture, it cuts out some locus in the space, and that locus is Z tau circ. Okay, great. And there are a few, there's one special type which I'll be interested in, so I'm calling it an essential type. And so it's one of these mod R types, one of these pictures which satisfies 2 extra constraints. So the first constraint is that, let's see which way around I want to write it. Yeah, okay, so I guess for all vertices in V0, so I guess V0 are just the vertices which I assign the red 0 to, so this V red 0, the corresponding like number in the vertex, so the genus of that vertex, has to be strictly positive. And the second constraint is that with respect to this decomposition of the vertices by this 0 and plus assignment, the underlying graph must be bipartite. So if we go back to the previous picture, I'll do examples in a second, but so this picture satisfies the first condition because the only vertex with a plus has a 1 inside of it, which is positive, great. But it doesn't satisfy condition 2 because of this edge here. This edge connects two 0 vertices to each other. So this is a 0 guy, this is a 0 guy, and so it's not bipartite. So this is not essential on this page, but I'll draw some actual examples next. So this is just a purely combinatorial condition about what these pictures look like. But the reason this is useful is okay, so this is one theorem, my thesis, which is like, actually these types classify all the irreducible components of this space. So what is this bijection? Well, you take a type, tau, and you just take the associated stratum as defined above, and you take its closure. So the closure of this, and the claim is that that's every irreducible component arises uniquely in this way. So okay, that's nice. Let's just see what this theorem says for like low genera. And then we can draw some of these pictures and see what's going on. So in genus 0, there is precisely one essential type. So what does this type look like? Well, I have one vertex of genus 0, and I have to label it with a 0. So it's pretty boring. And then I have some legs, but I'm going to omit those because the legs just have to be attached to this vertex. Like there's nowhere else they can go. The legs meaning the things corresponding to the marked points, but so there are like n of them corresponding to n marked points, but that's somehow actually not it doesn't really matter for now. Great. So, but what does that imply? Well, that actually implies that the moduli space, this universal space, is irreducible. Or AR is irreducible. This was actually first known by Abramovich, Cadman, and Wise in 2017. So they prove it a different way, but that was a part knowing it was irreducible is an essential part of proving that these two types of invariants agree. So these integrals in this Orberford setting equal kind of the integrals in of this other compactification. So okay, we will cover that. For genus 1, well, there is still a kind of so-called trivial type where I just take a single vertex of genus 1 and I associate a 0 to it. So maybe I'll call this tau. So we have this picture as before, just with the zeros changed to 1. But now we have like many more interesting types. So we always have the following pictures as well. Yes, and then I need to tell you what the assignment is. This guy is a plus. These guys are all assigned 0. And you can check this as essential too. And maybe there are k of these kind of guys, and maybe you can denote this by tau k. So that now there are infinitely many irreducible components to the space. So it suddenly goes from something irreducible in genus 0 to something like drastically, it's not even finite type for like genus bigger than 0, but Maybe I should draw as well. Like, what is this kind of geometrically saying? So I need to tell you what the kind of dual picture to these are. So the dual picture to tau, it looks like just smooth genus one curves with like a line bundle section pairs, which is not identically zero. Great, so that's simple enough. And that's one of the nice irreducible components. But these tau k's is parameterizing like curves which look like genus one curves with a k rational tails. So sorry. Oops. So now there are k rational tails corresponding to these k vertices labeled 0. And the section has to vanish on this elliptic curve, but it can't vanish on these rational tails. So somehow these loci are like big enough to not be included in the closure of the kind of smooth of a locus with things with smooth domain. So there's something funny going on. Yeah. Any questions about anything?
So you say there's bijection between irreducible component and essential types. How can we say about non-essential? Is it intersection between irreducible component or something else, or we can't say?
Oh yeah. Yeah, no, that's a very good question. So right, okay, so you caught me out as well. So the answer is like almost yes. So these non-essential types do occur as intersections. So all non-essential types occur within, okay, so maybe I'll say this is that like as defined so far, these Z tau circs don't form a stratification of the space because yeah, if you intersect two of these strata together, you don't necessarily get a union of kind of other Z tau circs. But there's some additional like extra discrete data you can fix. So basically I'm just trying to say there's a slightly more general definition of what a mod R type is, and there are kind of like more refined strata. And then in that case, all of those do occur as like intersections of these guys. But as written so far, if I intersect two of these like irreducible components, I don't necessarily get like a Z tau circ for a non-essential type. But there is a way to fix it just by adding in a little bit more discrete information, which I've omitted. Tell me if I can explain that better.
Okay, thank you.
Yeah, thanks a lot. So yeah, the answer is like you're right up to including more discrete information, but if we're just talking about the maximal strata, the irreducible components, you don't need to worry. They're all as I wrote. Yeah. But yeah, I mean, like for example, like yeah, you can understand what the intersections of these irreducible components look like in terms of so for example, you can say when two of these guys intersect in a non-empty way, and kind of the idea is you want to come up with there's a notion of specialization of type. So if I have a graph, maybe I'll draw a little picture. So maybe I have a graph which is like I don't know, like this. Imagine this was my domain graph, and I can contract this edge E, and I might end up with this graph. I've been as okay, I can construct like strata from kind of both of these pictures, and the idea is that like the stratum associated to this will intersect the stratum associated to this. So it's related to like which kind of data specializes to other data, and you can describe the intersections that way. But it's not always just like a unique stratum or something. There could be many things in the intersection. Yeah, thanks.
Thank you very much.
Cool. So yeah, so you can actually say more. So this now is about the structure. You can say something about the structure of like many strata. So this is not just for essentials. This now we can think about any stratum. And okay, so here's a setup again. Like let's take a point inside of a particular stratum and the decomposition of the vertices. So I said there is like a labeling of the vertices, the plus and or 0 and plus. That gives a kind of a way to decompose the domain curves in this locus into something which I'll call C0 union something which I'll call C plus. I mean, like here's an example. Okay, maybe I'll quickly go back to the example and do it. So basically, I just take the piece of the curve, like the union of the components which are labeled with 0 is C0, and the union of the guys which are labeled as plus is C plus. So in this page here, I want C0 to be the two rational guys because they are labeled as 0, and C plus is just this genus 1 curve because that's for anything labeled as plus. So that's what I mean by this notation. So that's just in this particular example. But in general, yeah, you've got a C0 and a C plus. And so here's the idea to understand the structure of these strata is that if I look at the restriction of the line bundle section pair to C0, this line bundle section pair is uniquely determined by this discrete data lambda. So somehow on the locus where the section doesn't vanish, there's actually no freedom in the line bundle section pair. It's basically just the curve. However, if we instead look at the restriction to the locus where the section does vanish, so this is now just L restricted to C plus and 0, because the section is identically 0 on C plus. This is determined by lambda, but only up to a twist. So only up to I guess a twist. So in other words, so the line bundle is uniquely determined up to twisting by something further. And I'll say a little bit about this, but the key point is this, okay, kind of a formalization of this is the following theorem, is that there is some abelian, so some semi-abelian variety. So think of, okay, semi meaning there could be some tori, so like GM or C stars to the whatever, cross an abelian variety, which acts on this locus, and it makes it into a torsor. So it's a free intransitive action on the locus where I fix the actual domain curve. So I guess in this locus, really the curve could be changing, but if I look at the sublocus where the curve is like a fixed guy, this is a free intransitive action. And this notation for this abelian guy, so a semi-abelian guy, Jack C plus, is really just like, it's because it's really built from the Jacobian of C plus. So so here's a first approximation. So here's like, so think that Jack C plus is approximately actually equal to the Jacobian of C plus. Oh, sorry, yeah. Okay, so maybe I can yeah, I should draw a picture. Maybe I can even insert a new page. New page. Okay, I guess I can always zoom in and make it visible. Okay, so let's zoom in and I'll draw a picture here. So here's kind of what the theorem is saying in terms of a picture. And shout at me if this is too messy or it makes no sense. So let's look at genus 1. And let's consider like, so I said what a few of these essential types were. So I had a tau which was just a single vertex labeled, oh sorry, it's a single vertex labeled with a 1, and the assignment is 0. And then let's just take a particular other guy. So I guess it's a tau 0, which is a 1 but labeled with a plus. So I'm going to draw a picture of what the kind of corresponding, so these are two essential types. I'm going to draw a picture of what the corresponding irreducible components in a moduli space look like. So we have some locus like this, and kind of meeting it transversely is another locus. So this bottom piece is going to be z tau. This top piece is going to be a z tau circ. And now I'll tell you explicitly what points in this locus look like. So let's take a generic point in z tau. It is just as we kind of said before, a smooth genus 1 curve. The line bundle is explicitly O of the sum of Ci Pi, so the Ci's are just the contact orders, and S is just the section cutting out the Cartier divisor, sum of Ci Pi. And so there's no moduli aside from the curve. So given the curve and the contact data, like there's no freedom aside from, which scaling of the section we have. And now what happens is that we can imagine moving towards the boundary of the stratum. So there's maybe something over here. And we can move towards the boundary by kind of scaling the section to be 0. So in this kind of boundary locus, we still have a smooth curve, and we still have this line bundle. But now we have the 0 section. So that's allowed. That's also in the space. But now, because of section 0, we've got a new degree of freedom. So now we can bubble off the main this component into a new one and kind of move along this kind of green locus. So what is a point up here? Again, a smooth genus 1 curve. But now the section can be, sorry, the line bundle can be twisted by anything in the Jacobian. So J is in Jac of this elliptic curve. So the idea is that this green line, it looks like a copy of the Jacobian of the domain curve. And so over this kind of boundary locus here, this theorem is kind of saying that this whole component looks like a universal Jacobian. And it's just generalizing this to kind of the other components as well. But this is really like the key point, is that it's built from kind of the main locus and kind of boundary loci of that, along with like universal Jacobians over them. And that's what every component, every stratum looks like. Great. Any questions about that picture? Hopefully it was visible. But... Okay, I should check actually, like how much time do I have? Like a half an hour or something? Or...
Yeah, you have half an hour more. Yeah.
Okay, great. Yeah. Okay. So yeah, so somehow like we understand completely the structure of this space in terms of combinatorial data and what like each of these combinatorial loci looks like. Is some abelian variety and something which looks like some part of the moduli of curves, some boundary stratum of the moduli of curves. So okay, it feels like we were far away from our motivation of trying to understand the general structure of these invariants. So let me talk about how this can explain, the original property that these invariants are polynomial in the routing parameter R. So let me say something about this. So the first is that let's pick a lambda and n. So it's just an initial choice. You could take lambda to be 1, but yeah, there's something that, and there are maps between these moduli spaces as we kind of vary the routing parameter. So there's a map from the one with parameter lambda times r to the one with parameter just plain lambda. And let me just write down what it looks like. So a guy upstairs is, again, a curve, twisted curve with a line bundle section pair. And what I'm going to map it to is the same curve with the rth tensor power of this line bundle section pair. And so somehow you can check that, like, yeah, so that actually does live in the right-hand space. Maybe just a sanity check, if lambda is 1, then what this is doing is saying that like we basically take the like, so this half tensor power is something pulled back from the course space, and yeah, yeah, you technically have to do something with the curve as well, but it's not so important. It's basically given by the tensor power, the tensor product of like bundle section pairs. Great. So okay, here's a nice result. Is for this map. Firstly respects the strata, so it sends one of these loci upstairs to a stratum downstairs, and okay, you can explicitly say which mod R tropical type is the image one, and what mod R tropical types are mapped to your guy downstairs. That's yeah, so send strata to strata. And also you can calculate the degree of this map restricted to a stratum, and it's actually a monomial in the routing parameter. Actually, here's a little typo. I changed my lambdas to r's, so this should be a oops. There's the degree of pi r, and this is a c r to the k tau. K tau is just some number depending on the stratum, and it lives between 0 and 2g minus 1. Okay, great. Let me just say what this k tau is really doing is that this map pi r looks like a map between kind of abelian variety torses. So there are these components built from abelian varieties and a map between them. And fiber-wise, it just looks like multiplication by r in the abelian variety. So, well, what is the degree of a map between abelian varieties by when you're multiplying by r? It's just the torsion. So this is in terms of the R torsion of the abelian variety Jack C plus that the strata are built from. And okay, so what is something we know about the torsion of Jacobians of curves? If I have a smooth genus G curve, the R torsion is of size 2, sorry, it is size R to the 2G. So that's more or less this 2G minus 1 here. There's a discrepancy for some stuff. It's not equal to the R torsion exactly, but it's related to it. And what happens, so here's a little example. It's just, I kind of like this, is that what is the Jacobian of an elliptic curve, or the R torsion of it? So the Jacobian of elliptic curve is an elliptic curve with R squared R torsion. And if you degenerate the curve, so maybe I take a nodal genus 1 curve, this is now actually just C star or Gn. And this now, well, okay, what is the R torsion in C star? I just have a roots of unity. So now I get a lower degree monomial. I get R. So kind of the idea is, what does this theorem say is that if I sum up all of these degrees over different strata, by the, due to the different topologies of the curves and how degenerate they are and stuff, we get a polynomial in the routing parameter of degree between 0 and 2g minus 1. So kind of a formal way to say that is that we can push forward the fundamental class of our space via this map, and it's polynomial in the routing parameter. And the coefficients of the polynomial are really Chow classes in this space. They're cycles in this space. But yeah, it's really just it's just saying this observation that you're summing up different monomials. Great. Yeah, any questions about this?
Could you maybe briefly repeat again what you wrote in the box and what you said in the box when you didn't quite, like in this box on the right margin?
Yeah, sure, of course. So okay, this theorem says that the degree of this map between the two strata is like a monomial in the routing parameter. And the exponent of this monomial, I'm saying, can be computed or related to the R torsion of some abelian variety. Basically because of the structural results here, like somehow the space is built from abelian varieties glued to each other. And this map pi r is kind of akin to like multiplication inside of this abelian variety. And so the degree of multiplication in an abelian variety is the same as counting the torsion points. So there's some way of relating, I guess, r to the k tau in terms of the r torsion in an abelian variety. And we just know from kind of the geometry of curves that the r torsion of the Jacobians of curves is like a monomial. It's like r to the something related to the genus. So that was me very messily paraphrasing in the box.
No, yeah,
but
now it's clear. Now it's clear. Yeah, thank you very much.
okay, great. Cool. Yeah, but so that's kind of really I guess everything I said out loud was the idea of the proof. So you have to know that the structure of these guys is abelian varieties, and this map looks like multiplication in abelian varieties. Great. Yeah, thanks a lot.
Maybe another quick question about this pi r.
Yeah.
So is it about its surjectivity? Is it surject?
Yeah, that's a good question. So it is surjective. Basically because so basically what you need to show is if I have a curve with like here's a simple example to convince you it's surjective. Imagine this is my curve kind of inside of a right-hand space. My groups look like, sorry, it's a mu lambda because I got parameter lambda here, and maybe my line bundle looks like I can write it as O of like 1 over lambda times a point. So I think of this red point here as 1 over lambda times a point, where like this point is really like, you think of it as a point from the core space, and if you pull it back, now we have like a fractional version of it. So the line bundle, like it basically the picture is a root stack, and that's why this notation makes sense. This actual curve itself is a root stack. And kind of to show it's surjective, you need to draw a curve upstairs with labeled with group mu of r times lambda and a line bundle. So I need an L such that L to the r is isomorphic to O of 1 over lambda times p. And well, I can kind of do the naive thing and take L to equal O of 1 over lambda times r p. So when I'm taking like the r power, I'm just cancelling off the 1 over r.
Yeah, I see.
And that's more or less why it's surjective. It's like, yeah.
Yeah,
But
thank you.
yeah, so that's a good question. Cool. So yeah, there's some stuff about root stacks going on there about if you do like an R root stack of something, and then you do the Landolf root stack of that thing, you get actually the R times Landolf root stack of the original thing. So there's some compatibility. Yeah. Thank you. So I'll be a little bit brief about this. This is kind of so yeah, what I wrote previously is I guess I put a paper out like maybe last month or in January. To actually deduce what you want to about the original enumerative invariance, there's some kind of like missing deformation theory arguments, which okay, people often say is like virtual geometry. I'm not gonna. I basically I'll say what. So that there's a project I'm finishing now with Sam Johnston, which kind of upgrades this. So, okay, the previous corollary is that the push forward of this class is a polynomial I'm a routing parameter. Great. There's actually another class which you need to work with for the purpose of enumerative geometry, which is a virtual class. So, kind of what one of the things I need to show, what I'm showing with Sam is that there is something called the virtual class. So there's a little subscript, and we really want this guy to be polynomial, not the fundamental class. I won't if you can ask me at the end, but it's a more subtle class than just the fundamental class as it incorporates something more about the deformation theory of objects in a moduli space. So it's more complicated than just the fundamental class. But there was, yeah, I'll say like one of the key inputs to this is that this moduli space we're interested in. So I guess think of X here as like just take it as for the space of maps we're trying to understand. It actually embeds into something which looks smooth. And so more or less in a way we can describe it by explicit equations inside of a smooth space. So that it embeds into some type of universal Picard stack over another space. Don't worry about it. So it embeds into some universal Picard over a so-called log smooth space. I won't bother writing details in that second green box. It's probably just, you can ask me if you want more information. But the idea is that this moduli space now we kind of have some explicit equations for, and then you can actually understand this more like subtle virtual class from this, and you can deduce the same result. So maybe okay, I'll probably finish like very soon, but let me just say out loud some applications of this I'm doing, what will be in this paper with Sam, is that, well, I guess for now, it's like I said that the divisor is smooth. And actually, that's a really big part of this, is that like the divisor needs to be smooth, or actually a bunch of the theorems like kind of break down. So what we do is we generalize these results to kind of a higher rank setting. So the higher rank setting just means I have general like simple normal crossing pairs now. So the divisor can have many components that intersect with each other. The interesting thing that happens is that, well, when the divisor is smooth and genus 0, we said for spaces that this universal space is irreducible. In genus 0, if you have more divisor components, it actually might happen that the space still has many irreducible components. But the fix is that if you kind of blow up enough the target, these extra components disappear. So yeah, so maybe I'll just say it's that like for more general divisors where you have more components, as I described before, you can look at kind of the question of counting maps to that pair where you fix tangencies among, like, say, different components of this divisor and you fix them. And there is some corresponding orbifold enumerator theory for this guy. So that didn't really need, the sense that didn't need the divisor to be smooth. You can try and count maps in the same way. And there are these moduli spaces. Now, it turns out these associated invariants are polynomial in the routing parameters as before. And we show that if we additionally blow up the target enough, that the constant term recovers these other known invariants, these log Gromov-Witten invariants. But yeah, the extra subtlety is that like you might have to blow up your target first to make this work. This is related to the second point, which is, okay, more down to earth is saying like there are formulae for certain invariants. So maybe I'll just write this down below. Is that so Gromov-Witten classes are, well, I can look at this space of maps, orb of xd, or maybe I'll just look at, say, you can look at just stable maps to a target x. So there's no tangency or anything now. I'm just kind of looking at maps which pass through various like cycles in X, and there's a space of stable maps. This has a forgetful map to just like MGN. And you can, Gromov-Witten classes are of a fit form kind of push forwards of certain cycles on the space of maps. So alpha is a cycle on this space of maps. The statement that these classes are tautological is basically equivalent to say you can get like formulae to compute them. So there's a kind of a nice subring of the cohomology of MGN, which is, okay, the tautological ring, and these are kind of classes which have very explicit like multiplication rules and relations, and you can get a hold of what they are. And there's a big conjecture that these classes are, all these push forwards of alphas for spaces of maps actually lie in this ring, so have formulae basically. And what this kind of first bullet point can allow you to show is that if your target can degenerate to something, say, which looks like a union of toric varieties, you can deduce like a bunch of these classes are tautological for like any genus. So there's some argument which goes through all of these orbifold and whatever theories and all these previous results, which allows you to get this. And okay, the last bullet point is there are you can get other interesting classes like cohomology classes in MGM-bar by applying this to this kind of understanding of the polynomiality of the fundamental class to certain targets. So if you apply these results to like P1 with the divisor 0 and infinity, you get some classes related to double ramification cycles, which are other well-studied like loci classes in moduli of curves. Yeah, okay, I think I'll leave it there. Yeah, and let me know if you have any questions.
Yeah, thank you very much. Thanks for the nice talk. So is there any questions from the audience?
So I've kind of forgotten like the invariance of GW. Is it a invariance on the original space of twisted maps, or is it an invariance on like the universal space? Because I don't know. Because the
yeah.
only place you mentioned that they are polynomial is that the child class on the universal spaces.
Yeah.
Yeah.
That's a really, really good question. And I skipped saying, maybe I'll say what the relation is between this polynomial stuff on the universal space and because I at some point I was like, oh, I just tossed away these original spaces and I worked with the universal guy and I never went back. So there was a way to go back from the universal space. And let me just kind of summarize why. We really want to understand this space for like a given x and d. But instead I said, oh, let me study this space, the universal space. It turns out there's like a Cartesian diagram relating them. So there's this forgetful map and oh yeah, okay. So this left-hand side maps to just stable maps to the target X. Just by I forget all the orbifold structure, I forget all the contact orders, and I just forget maps to X. And this universal space maps to just like kind of curves with line bundles and sections subject to like no conditions really. There's again a similar map and also a map from here to here. And there is a Cartesian square relating these. So basically, the space we actually want to study is a base change of the universal space. And the idea is that if you prove relations in kind of the cohomology down here, we can pull them back and get relations up here. And so for example, these like fundamental classes we wanted to study up here are actually just the pullbacks of the corresponding fundamental classes down here. So the general structural result about being polynomial is preserved under, like you can deduce it upstairs from knowing it downstairs.
Yeah, thank you.
Great, thanks.
And also, like, you have nice stratas on the universal space. So, I mean, given any space of the twister map, do you know what the pullback of the stratas are?
Yeah, that's also a really good question. So I do like, there are a few examples I have at the end of the paper. the thing is that like I mean, the pullback of a stratum in general, actually, like even if it's like irreducible, the pullback of a stratum upstairs has like many connected components. So I can draw you a little picture for like genus one. Sorry, it's kind of like, oh, okay, that's really bad. So this was like for, something inside of a universal space for like genus one, and I had these green fibers which look like kind of the Jacobians of like some elliptic curve. And then maybe there's like an actual space. This is kind of inside of orb of XDR for some target. And that maps down to this guy. This main stratum pulls back to like an irreducible component. But if I pull back for kind of this other component, all I'm doing is I'm somehow just seeing like the R torsion point. So I don't get the full green line. I get like a bunch of disjoint copies of things which are indexed by kind of, I guess, yeah, in this case it'll be kind of 0, 1, 2 to R squared minus 1. So somehow like, yeah, the strata upstairs are like further decomposable by like the torsion. You don't see the full Jacobians now.
Okay, thank you.
So any other questions from the audience? So maybe trying to understand how this thing with the blow up helps. So in the beginning, we had this assumption that D is smooth, but it can have several connected components. Is that the reason why you can then
Yeah. Yeah, okay, that's a good question. So I'll tell so this okay, I'll tell you like a tiny bit of history. Which isn't me. It's like I didn't do this. This was like known, but this is even a genus zero phenomenon, which is so in genus zero, what do we have? So if D is smooth, we said that kind of orb of AR is irreducible. And then I said there was some other space which I didn't write down, but there's another compactification or another universal space called log of AR, and that's also irreducible. But if D is
here D, sorry, here D can be not connected, right? It doesn't matter, or
yeah, that's a good question. Yeah, D can be like a disjoint. Yeah, if you have
right.
disjoint guide, yeah, you
Okay,
can
I
do
see.
that as well.
Yeah.
But if D is kind of not smooth, so think about like P2 with like two lines, D1 and D2. What it turns out is that this log space is still irreducible, but now the orbifold space can be reducible. I'll just write because it depends on the exact contact orders and stuff, but can be reducible. So somehow in genus, if I have like D not smooth in genus zero, these two like theories just can't agree because like one is irreducible, one is reducible. But here's the fix: is that like if I first blew up enough, so in this example, you might blow up this zero stratum or P2, and you've got some exceptional, oops, you've got some exceptional, and now you have three components. Maybe I'll write D1 tilde E and D3. We can consider the, sorry, I guess throughout, ignore AR, I'm going to write, this you can think about the geometric targets. So you can think about X, dr, and log of X relative D, log of X dr, log of X relative D. Sorry, yeah, ignore the universal stuff. on this blow up, we can consider, orb of kind of x. Maybe d tilde is just d1 tilde plus e plus d2 tilde. This can now be smooth, so is irreducible again. So basically what I'm saying is that like for your initial enumerative problem, like for example P2 relative 2 lines and counting maps with some particular tendencies, these two spaces might look very different, but if we then blow up the target in some strata of the divisor, we can make the spaces look the same again. And then the invariants agree. So yeah, let me know if like that didn't make sense.
Yeah, I think so. So the idea is then that you translate kind of tangency conditions and the intersection point in D1, D2 into tangency conditions D1 tilde, D2 tilde, which now are disjoint. So now you're in the case of D smooth again, and that's why. Is that more or less?
Yeah, exactly. Yeah, so somehow like it's only the problems are like when you have tangency to like the deeper strata. And like basically the idea is if I had a tangency condition to like the intersection of D1 and D2, weird stuff can happen. But if I blow up, I can then force those tendencies to be like transverse to like this exceptional divisor and away from any deeper strata anymore. So
I see,
in that
yeah.
case, like everything behaves as like a smooth case. But yeah.
I see. Yeah, thanks. And then this, you said it can be. Sorry?
No, go on. Sorry.
So you said it can be irreducible sometimes still upstairs. So the orb XDR, if D is not smooth. So is it something like if the tangency to D1 and to D2 are coprime numbers, then it's irreducible or something like this?
Okay, maybe I'll say it like here's an example is like so maybe your question is like what blow up makes this
Sorry, no, my
reducible?
question
Yeah,
was because you said it can be reducible, but I interpret that you're saying it can also be irreducible sometimes.
Oh
Or-
yeah, the downside side can be reducible, and like you should think of it as like you know it's gonna be it's not an if and only if, but it is irreducible precisely when you aren't looking at tangencies to deeper strata. So if I wanted to count curves which just kind of hit D2 at like at this generic point and sorry, D1 at some like point and D2 at another point away from this red point, it is going to be irreducible. But instead, if I wanted to look at maps, so here's my picture of P2 and 2 lines again. If I wanted to look at maps which like go through this red point, that's when stuff can go wrong.
I see. Okay. So if you impose some weird condition like the curve maps, it's tangent to D1 with tangency 2, for example, at the point of intersection, and tangent to D2 with tangency 3 at the intersection.
Yeah, you could do that, or just like tendency 2 and tendency 2 with each of the divisors, but kind of at the same point. That's like when stuff
Okay.
goes wrong. Because I guess like you kind of when you have more components, you specify the tendency by like not a single number now, but you might specify it with like an A, like a tuple A and B, where this you should think of like tangency to D1 of order A and okay, D2 to order B. So if you have just like 1, 0, that's saying actually you have 0 tangency to one of them and some tangency of one of them. So it's kind of it can't intersect a red point, but if you have like 1, 1, that's saying you must go through this red point. That's kind of how you would encode it.
I see.
So
Yeah,
but
so I
I
guess
guess the problem
I see.
Mhm.
Yeah, sorry.
Oh, I was just saying, so notationally kind of in this language, it goes wrong when both A and B are like non-zero at the same time.
Right. Yeah, I see. Thank you. Yeah. Okay. Any other questions from the audience? No, then yeah, let's thank Robert again for the very nice talk. Thank you very much.
Thanks a lot.